Hello, everyone. Today in this video, I will go over with you chapter 15, which is all about chemical equilibrium. I have your notes here on my camera, and so I'll go through this with you, do a little discussion, and work a few problems all about chemical equilibrium. So chemical equilibrium occurs when opposing reactions proceed at equal rates. What this means is that the rate at which the product forms from the reactants is the same as the rate at which reactants form from the products. So we're going to have chemical reactions that are able to proceed both forward and backward. Equilibrium state is a mixture of the reactants and the products whose concentrations are no longer going to change with time. So this means that your reactants and your products, the concentrations of those don't change. We can still have reactants forming to create products and products conforming to create reactants, but since they are occurring at the same rate, the concentrations of those don't change. So this equilibrium mixture results because, like I mentioned, the reaction is reversible. So we have both forward and backwards reactions occurring at the same time. And when we have this type of reaction, we illustrate it like this with these two half arrows that are pointed in opposite directions. This tells us that we can have this dinitrogen tetroxide here forming nitrogen dioxide at the same time that the nitrogen dioxide is forming the dinitrogen tetroxide. Okay. So once equilibrium is established, the concentrations, like I mentioned, no longer change. Okay. So the concentrations of our reactants and products no longer change once we are at that state of equilibrium. The fact that the composition of the equilibrium mixture remains constant doesn't mean that we stop the reactions. Okay. The equilibrium is dynamic. So when we talk about having dynamic equilibrium, what we're talking about is that some reactant is always converting to product and some product is always converting to reactant. Just at equilibrium, the processes occur at the same rate. So equilibrium, again, it does not mean that the reactions stop. It just means that they are occurring at the same rate. So the forward reaction and the backward reaction are occurring at the same rate. So 3 takeaways from this section. At equilibrium, the concentrations of reactants and products no longer change with time. For equilibrium to occur, neither reactants nor products can escape from the system. So we have to have a closed system or a system where we are collecting all of. The third takeaway is that at equilibrium, a particular ratio of concentration equals a constant. And that's what we're going to get into next. So a reaction in which and I just noticed an error in my note. You know, I read over these and never find them until I'm going through it with y'all. A reaction in which the reactants convert to products and products convert to reactants in the same reaction vessel, so in the same system, naturally leads to an equilibrium. So when we have some type of reaction that can proceed both forward and backward, if we put those reactants there together in a closed system, then we're naturally going to achieve equilibrium. And this doesn't matter on how complicated the reaction is, how many steps may be a part of it, or the kinetic processes that occur. It doesn't matter. They're naturally going to reach equilibrium. We have a law that helps to kind of govern this or explain this and allows us to derive our equilibrium constant. And this is called the law of mass action. And the law of mass action is going to express the relationship between the concentrations of our reactants and products at equilibrium for any reaction. So if we have this generic reaction here, then according to the law of mass action, the equilibrium condition is described by this expression. So we have our equilibrium constant here. The products are on the top, the reactants are on the bottom, and the concentrations are raised to the coefficients of each. And this expression is called our equilibrium constant expression. Okay. And sometimes you'll see this as just the equilibrium expression. So the equilibrium constant expression, or the equilibrium expression for the reaction. And so the constant, like I mentioned, the constant K sub C is the equilibrium constant. And it is the numerical value, so its definition is the numerical value obtained when we substitute the molar equilibrium concentrations into that equilibrium constant expression. And because of that subscript C, that represents concentration. Okay, and just like before, we're going to express concentration in molarity. Okay, remember molarity is moles per liter. So the numerator, that is the top number in that expression, is the product of the concentration of all substances on the product side raised to that power of the coefficient. And then the denominator is going to be our reactant side. The equilibrium constant expression depends only on the stoichiometry, not on its mechanism. So in the last chapter, we discussed reaction mechanisms, and we talked about elementary steps. We talked about intermediates that may be formed. We don't have to worry about any of that with the equilibrium constant expression. We are only looking at the stoichiometry, not the actual mechanism. The value of the equilibrium constant at any given temperature does not depend on the initial amount. Okay, so it doesn't matter what our initial amounts of the reactants and products are. The value of Kc is for that particular reaction and at that particular temperature. Okay. Sample exercise 15.1 walks you through how to set up these equilibrium constant expressions. So they give us a couple of chemical reactions here. So the first one, we've seen this one a couple of times already here, as we've been working on kinetics and reaction mechanisms. So we have the conversion of ozone into atmospheric oxygen, the forward and reverse reaction, and they want us to write the equilibrium constant. So remember that the numerator is the product side, or the product concentration, raised to its power, and the denominator will be the reactant side raised to its coefficient. So that would be our Kc for the first one there. B, we have this reaction. Oh. And we will do the same thing for this one. So our expression, we're going to put our denominator on the top. So that would be NOCl raised to the second power over NO to the second power, and then Cl2 with no exponent because the coefficient here is 1. And then C, looks like this. And again, we'll do the same thing. Concentration of our product on top and our reactant on the bottom. So that is how we write our equilibrium constant expression. Okay. So moving on, the value for Kc is constant. It is called the equilibrium constant for a reason. It is constant even though these initial concentrations may vary, but the rate, or the constant, the equilibrium, is going to be constant. So it doesn't matter what our initial concentrations are. Now, when the reactants and products of a chemical reaction are gases, we can use this same expression to look at partial pressure. So we have the same expression, except we're going to use K sub P, which is for pressure. And then we use the partial pressures of each of the gases. Now, the partial pressures have to be in atmospheres. So as long as we have atmospheres for our partial pressure as the unit for our partial pressure, then we can use this expression and denote our equilibrium constant Kp. Now, Kc is generally different than Kp, so we don't expect the equilibrium constant and the equilibrium pressure constant to be the same, but we can extrapolate this expression and use the ideal gas law to switch from one to the other, where our Kp is equal to Kc times RT raised to the power of delta N. So R, of course, going to be our ideal gas constant, T here referring to temperature, because remember, Kc is dependent upon temperature. And then delta N is the change in the number of moles in the balanced chemical equation. So it would be the moles of the gaseous product minus the moles of the gaseous reactant. And again, this is only when we're dealing with gases. Okay, so we can convert between Kp and Kc if we have gases. And that leads us to sample exercise 15.2, which is on page 636. In this example, we're given a chemical reaction, which is for the Haber process, the conversion of nitrogen and hydrogen into ammonia, which is a reversible reaction, and we do have all gases. They tell us that our Kc is equal to 9.60. Our temperature is 300 degrees Celsius, and they want us to calculate Kp. So we're going to use this formula here. So Kp is equal to Kc times RT raised to the delta N. Okay. So our temperature is in Celsius, and if you remember from the ideal gas law, anytime we use temperature with the ideal gas law, it has to be in Kelvin. So we're going to add 273.15 to that to get it to Kelvin. So let me plug in here. I've got 9.60 for my Kc. Then I have my ideal gas constant there, 0.821. And that's going to be multiplied by my Kelvin temperature, which is 573.15. And then I've got to get my delta N. So delta N is the moles of the gaseous product. So I look at my coefficient, I have 2, and then minus the moles of gaseous reactant. You know, if we don't have a coefficient, that means 1. So 1 plus 3 is 4. So 2 minus 4. So delta N is -2. So I'm going to raise that to the -2 power. Okay. Now, I can work this one of two ways. I can multiply these, go to the -2 power, and then multiply by 9.6. Or I can get to a positive exponent here by putting it as the denominator. That is the route your book takes. It really doesn't matter. You're going to end up with the same answer anyway, whether you just work it straight across or whether you do it like the book does. I'm just going to work it straight across because to me that makes it a little bit easier. So I'll go to my calculator and I'm going to type in 0.0821 times 573.15, enter, and then I'm going to take that. So that gives me a value, and I'm just going to jot it here so I have it. 47.056, rounding. And I'm going to raise that to the -2 power. And so now that's going to give me, you see the value here. And now I've got that value raised to the -2. So I'm going to multiply that by 9.60. And that gives me 0.00434 as my answer. Okay. Now, we have 3 sig figs here in our Kc, so we'll have 3 sig figs here. You can leave it just like this, or you can put it in scientific notation, which would be 4.34 times 10 to the -3. Now, as you see, as I wrote this down, the equilibrium constants are reported without units. Okay, because they're defined in terms of the activity and not the concentrations or partial pressures, because Remember, it doesn't matter what our initial concentrations or our initial pressures are. We're only concerned about what is happening, what is happening at equilibrium. Now, we move into understanding and working with the equilibrium constant. So what we're concerned with in this equilibrium constant is the magnitude of the constant, because that's going to give us information. If K is large, so if it's a lot greater than 1, okay, so if it's greater than 1, equilibrium lies to the right, the products predominate. If K is really small, then the equilibrium lies to the left, the reactants predominate. Okay, so what that means is that it favors one direction or the other. It is the forward and reverse reaction rates, not the reactant and product concentrations, that are equal. So keep in mind, we're not looking at concentration anymore. We are looking at just the reaction rates. So it doesn't matter where we have more concentration, we're looking at just the reaction rates. And the rates moving forward, so the reaction rates moving forward and the reaction rates moving backward are equal. We're not concerned with the concentrations at this point. They are not equal, and that's okay. We are just looking at the rate